everyone. We are moving right along here with transformations to talk today about our second type, which is going to be reflections. And this is going to start on page 112 in your book, and you're going to probably want a pencil and highlighter handy, possibly that vocab list that I attached to Google Classroom as well, just to kind of reference some of these terms. So if we look at this figure, and we've seen this figure actually before, but this time there's an extra detail added. So this time they're telling us that we have Maria marked at 2,4 on our graph. And then when the transformation of our marching cougars happens, Maria is moved to -4. Now, this is interesting because if we didn't have her marked, we might have said this was just a slide down a translation. But because of her location, she would be down here if this was a true translation down. What it is instead is a flip over this line, the x-axis, aka the line y equals 0 or the x-axis. Okay, it's a horizontal line through 0. So what we would say this is instead a reflection, which we call our flips, okay? And this is another type of rigid transformation that's going to keep the same shape, but it's just flipping. Notice a flip across this axis caused our y value to change. So when you flip across the x-axis, you change the sign of your y value, versus when we are going to flip across our y-axis, we're going to actually change the sign of our x value. And that's shown down here to us. Again, if we changed across the x-axis, again, we flipped the y value in each of these examples. But if we flip across the x-axis up here, the y-axis, so let's say we flip across here, we would change the x value, but the y value would stay the same. So all these x values get negated, as you would see down here. And again, that's shown by our function numerals changing that sign. Now, you also can reflect over other lines besides the x-axis and the y-axis. Those are just the two most common. A lot of times you'll actually see the line y equals x as well. That's just actually a flip-flop of your points. And that's important to you, especially when you get back into Algebra 2, when you talk about inverses, but not necessarily as important to our class. Now, on page 113, we have this arrow. And they want us to predict what direction do you think this arrow is going to land when we move it across the x-axis, so this line here, okay? Well, when we flip it across the x-axis, what's going to happen is it's going to flip so that it's the same direct distance away from that x-axis as the original arrow. But because of that flip, it's going to face downward, right? It's the same picture, but facing downward. On the other hand, what do you think happens when we reflect it across the y-axis? Well, our y-axis is again right here. And if we are trying to reflect it over that, what's going to happen is it's going to actually flip, kind of, if you want to think about it, over that, and it's actually still going to be facing upward. It's just going to be, and it's going to be that same distance again away from that axis that the original was. Okay, so we have downward for our flip across the x-axis, but the second one, the flip across the y-axis, was up. Now, what reflection is going to map the arrow so that it's facing downward but still has the tip at 4, 10? Well, if we go back to our arrow and we make it flip downward but still be focused have the same tip here, we want to think about what kind of line would it have to reflect over. Well, this is a horizontal line, so we know it's going to be y equals, and it's passing through the value of 10. Okay, so again, the x-axis is y equals 0. This one is a horizontal line through 10, so we would represent that as y equals 10. So this is going to be a reflection across y equals 10. And again, you're probably going to want to put on your cheat sheet of some sort is that you're going to have a vertical line is always going to be represented by x equals whatever number it's passing through. And then our horizontal lines, like we just saw here, those are going to be when we have y equals a number like we had here with y equals 10. Okay, so just remember kind of which ones are horizontal, which ones are vertical. Now, last but not least, could we officially have mapped this arrow so that it would have actually turned left or right? The answer is yes, but what you would have had to have done is mapped it across a diagonal line of some sort, which would just probably be like y equals x plus 2 or y equals negative x plus 2, with a negative slope. But we're not really going to talk about mapping it across those kinds of lines. But officially, you could kind of map it across any line. We just tend to like to deal with vertical lines and horizontal lines. Okay? All right, moving right along then. Notice we have a function rule. And if we start plugging into this function rule, let's say the tip of this arrow is at 4 comma 5. So we plug in 4 and we plug in 5. We're going to get 8 minus 4 is 4. 5 is going to stay the same. So really what we're noticing is that point is kind of staying the same place. On the other hand, if we picked a different point, let's say 2 comma 4, and we plug that in, what we would see is that the point is going to map to 8 minus 2, which is 6 comma 4. So it would map here. And if we looked at 2 comma 6, it would map to 6 comma 6. So up here. And then last but not least, if we mapped here, we're at 0 comma 5. If we plugged in 0 and 5, we'd be at 8 comma 5. So out here. So what we're seeing here is if we kind of look at our arrow as it mapped, we have a reflection again. But this time, if we draw in the line that it looks like it's reflecting over, it looks like it's reflecting over this line here. Now, a reminder, vertical lines are x equals, and in this case, it's passing through the number 4, so our vertical line would be called x equals 4. All right, so if we draw in that line of reflection and identify this, what we're going to notice is this is, again, going to have a line of reflection at x equals 4. Okay. And when we think about it, if there's a band member on that line of reflection, they didn't move at all. The people who moved the most were the people who were on the y-axis because they had to move all the way over here 8 units. So the people on the members on the y-axis traveled 8 units, right? Because they had to stay the same distance that they were away from that line of reflection. So 4 units to 4 units, right? So that's where that moved. Okay. Now, the tuba player who does not move any distance at all is this guy that is at the tip of the arrow, right? Whoever was positioned right here at 4 comma 5 did not move at all. And the reason being they are on the line of reflection. So they're not moving. Does not move. Okay. And that's going to be true anytime you have a line of reflection and a point on it. It was true in our last example on the last page when we talked about this arrow here. This still stayed put. And it's also going to be true if we look at another example here on page 115. Notice in the pre-image we had these points here on the line of reflection. They did not move when we reflected it. So again, points on the line of reflection do not move. Okay? So keep that in mind as you draw your lines of reflection. And if a point's on there, it's actually not going to move at all. All right. Now, something we touched upon a little bit the other day was that the notation for translations is how much you're moving, right or left first. We represent a translation with a big T. And then the x value, aka how much you're moving to the right or to the left, is represented there. And then the y value is your up or your down there. Okay, we talked about that. A reflection then has this lowercase r, and the line it's reflecting over then is located here. So this would be an example of reflecting over the x-axis at y equals 0, or we would say, okay, like we talked about before, a reflection over the line x equals 4 was like the last example we did. Here, notice we are reflecting over a line L. So we're going to draw in that line, and we're going to name it L. Okay? And when we reflect over this line, we see here that when we reflect, the points are going to stay, again, the same distance away from that line of reflection as they were originally. So B is going to map to B prime and be that same distance away. A is going to map to A prime so that that's where it's going. So notice they're talking about how original point P now becomes a prime. So that's showing us which is the image and which is the pre-image. So we have pre-image, image over here. And again, these points, okay, C was closer to the line of reflection, so is C prime compared to D prime. Okay, so always should be that same distance. Don't just recopy the points over here because it would not be the appropriate lengths away. The last thing we need to talk about then with lines and reflectional stuff is the idea of our reflectional symmetry and lines of symmetry. Okay, so something that has reflectional symmetry is going to be when we could fold it over the line of symmetry. So notice we have a couple different polygons here. Shapes here. And this first is an isosceles triangle that has one line of symmetry. And again, you want to think about where can I fold it so that it maps on itself. Well, think about a piece of paper here with this next one. Oops, a rectangle. I could fold this hamburger style or hot dog style. So it has two lines of symmetry. Now, officially, this star figure that is in our next picture here has not only through the points, but we could also officially, the way this is pictured, we could fold it over the these other lines as well, and it would map directly onto itself. So it has 6 lines of symmetry. Okay, these are all have reflectional symmetry, but different numbers of lines of symmetry. And not all shapes are created equal, right? Because we had the isosceles triangle here that had the 2 congruent sides. An equilateral triangle that has 3 congruent sides is going to actually have 3 different lines of symmetry compared to the isosceles triangle. Now, looking at the next page, we have a couple more figures, and we want to figure out, kind of match them, how many lines of symmetry do each of these have? Well, what we're going to see here is similar to what we talked about on the last page. The isosceles triangle here is still only going to have 1 line of symmetry. The rhombus, very similar to the rectangle we had on the last page, is going to have 2 lines of symmetry. Okay, because if we tried to draw one in here, it's not going to map directly onto itself. This is not going to be able to fold over here. Squares, unlike rectangles, when we try to fold them, we can fold them hot dog style, hamburger style, and then because of their equilateral type nature, right, because they're all the same size, this one officially you can fold with a square, not a rectangle, 4 times. And then we have the special circle situation, where as long as it's passing through the center of the circle, I could keep drawing lines all day if I wanted to, that there are an infinite amount of those lines of symmetry possible with our circle, given that circular shape. It's kind of special. All right, this last question here then is dealing with talking about why we have, when we look at this figure, why is BD not considered the line of symmetry? Well, we tried to make this the line of symmetry. And for instance, we drew in AB. If we tried to flip this over the line of symmetry, notice it's not going to map itself onto BC. So that's why in number 18, this is not going to work out, because when we try to map over that line of symmetry, it does not reflect to be BC. So when AC is reflected over BD, that line of symmetry, it does not map to BC. Okay. Now, kind of continuing on with that, if we look at this, is there actually anywhere that we're going to be able to draw on a line of symmetry? And the reason being, No. Okay, and the reason being is because the type of triangle that this is, it's called a scalene triangle. And what scalene triangles do is they have no equal sides in their picture, right? They're not like isosceles that have two or equilateral that have all three. There's no equal side lengths in this picture. So no matter where we try to draw a line of symmetry in this one, it's not going to work. None of these are going to map so that any of them are actually symmetrical. So does this have any lines of symmetry? No. Right? Scalene triangles have no lines of symmetry. All right. Thanks for following along with this reflections lesson, and we will practice more in class.